Hello students, welcome to Adantal. Good evening to all.
Good evening, sir.
Good evening, sir.
Good evening everyone.
Good evening, sir.
Good evening, sir.
Yeah, Arun, I'm good. How are you?
I'm also fine, sir.
Study of light is known as optics. And now we will start with geometrical optics. So these are the main three things that we are going to study first of all. Okay, but first of all, there is a simple rule associated when a ray of light travels from one medium to another, and that is called Fermat's principle. Okay, Fermat principle. This is called Fermat's principle of extremum path or least path. Okay, it states that a ray of light, when it travels from one medium to another, it may undergo any number of reflections or refractions. This is called Fermat principle of extremum path, along with the path taken is a minimum. Suppose there are 5 possible paths from A to B. Now, out of these 5 possible paths, the ray will take only that path along with the time taken is minimum. Of course, the first one, because we know that time taken during a straight line travel is a minimum, because that is the least distance, straight line distance between any 2 points.
Yes, sir.
So please go back to the first slide once again. Okay, sir, move on.
This is clear to all?
Yes, sir.
So by any number of reflections means
This also from one point to another.
okay.
So these are some of the important properties of light that we should know before starting the optics. And after that, we will study about the rectilinear propagation, laws of reflection, and laws of refractions. Please note down.
So can you explain point number 5?
Now suppose there is an incident ray and it is getting reflected. Okay, so then I mean to say, suppose v is the velocity, f is the frequency, lambda is the wavelength, then these properties they will remain same for the wave. Okay, and even during refraction, the frequency of the wave it remains same, but its velocity obviously changes. Okay, when it goes from one medium to another. Okay,
And the wavelength also undergoes a change in refractive.
obviously only one thing remains same because f is v by lambda. If one changes, then other also changes. No? If v changes, then lambda changes. So only frequency remains same, but lambda and v they will unchanged. They will be changed. Okay,
Sir, I did not got that point.
which point?
Your port relevant.
Velocity, frequency, and wavelength they do not change during reflection, and frequency it does not change during refraction, but velocity and wavelength they changes. That's what the point is. Velocity will change if you are representing it by v. Here you will represent it by v dash and lambda by lambda dash. Means frequency is the characteristic property of the body of the light which is retained during reflection and refraction. This is what you can remember as a fifth point. Yes. Okay. Is it clear now?
Yes, sir.
And in sixth point, I'm writing frequency of light remains unchanged during refraction also. But velocity and wavelength changes. Clear?
Yes, sir.
Yes, sir.
So these are the basic fundamental properties of light. So now let us study something about rectilinear propagation of light. So what do we mean by that, and when can we say that light actually travels in a straight line? Rectilinear means in a straight line. Okay. So now we will see whether light actually does this thing. Does it travel in a straight line or it deviates from its straight line path? Okay. So you can write the condition for rectilinear propagation of light. Let us see what is the condition to be obeyed by light. Okay. So the assumption that if the medium is isotropic medium means the properties of the medium they are same along different directions. This is the first point. The obstacle past which the light moves or through which the light passes, or the slit or some kind of opening, is not very small. Otherwise, diffraction effects they will be much more prominent. It means the width of the slit should not be very small. The width of the slit Okay, so now let us take one example and try to understand it with the help of one simple article in which we assume that light, when it passes through a slit of some particular width, then it deviates from its straight line path, and let us try to get the extent of deviation and when can we neglect that. Okay, let us try to get the condition. Now, here is a slit. Okay, so this is a straight line path just in front of the slit, but light, after passing through it, it follows this kind of path. Both ways, obviously. This. So if light travels in straight line, then it should have followed this path. Let us suppose this is the width of the slit is A. Okay, and the distance covered on the screen when it passes through the slit, it is B. And this, when you make this line meet that point, this angle is theta. Means this is the angle of deviation. And here the light was coming like this. And this is capital D. Okay, so consider a slit of width A through which monochromatic a screen placed at a distance D from the slit, as shown in the figure. Okay, so now can anyone tell me what is the deviation? How much is the deviation?
D.
Angle theta.
No, I'm asking you about the length of the deviation, value of the deviation. Theta is the angular, na? That is not the not in terms of length. Yeah.
Sin theta.
Theta then bata jayega.
No.
Lambda capital D upon small.
Can I call it B minus A by 2? Because B minus A is the deviation, total deviation, and along each side it is half of it, na? Isn't it? Is it clear or not?
Yes, sir. Clear.
This is B, this is A. So how much is the deviation? Total is the B minus A, na? So on one side it will be B minus A by 2, na? It means this much. I'm calling this as deviation, B minus A by 2. Similarly, this much also. Okay, I think it must be clear now.
Yes, sir.
We find that the deviation of light on each side of the central line is B minus A by 2. Okay, so now we will make use of theta. So now we know the actual deviation. Now with the help of theta, so can you tell me about actually it is the case of diffraction, na? Single slit diffraction. So what is the value of sin theta in a single slit diffraction pattern? Anyone?
Lambda by D.
Lambda by E.
A32.
Lambda by A, na? Okay. So now for small values of theta, you know that sin theta, it is nearly equal to tangent theta also, na? Because both sin theta and tangent theta, they are small and they can be written as theta only.
Yes, ma'am.
Means we are assuming that the deviation is actually very small, so that we can say that the light travels in a straight line. So it is a case of means negligible deviation. Okay. What I was about to write. For very small theta. And what is the value of tangent theta? This, na? Perpendicular over base, and perpendicular is B minus A by 2 and base is capital D, na? So therefore B minus A by 2D, it is nearly lambda by A, na? So B minus A by 2 is B lambda by A, na? Please check. Clear? So clearly the bending is negligible. Bending means this factor. When can you say that this is negligible?
Very less.
If it is less than A, na, the actual width of the slit. Am I right?
Yes, sir.
If this deviation is negligible as compared to the actual size of the slit, then I can say that this is negligible. Suppose it is 1/20th of that, 1/10th of that, right? Okay. So here you got the condition. Means A, that the width of the slit should be very, very greater than this value. Okay. So this is the condition for rectilinear propagation of light. Negligible deviation means straight line. No? So a question can be asked on this straight away.
So it is the Fresnel distance.
Yes, definitely. You call it Fresnel distance. That's how it comes. Normally in your books, I think they write it straight away. And they represent it by Z, I think ZF. In most of your graduation books. Fresnel distance. Clear? It means geometrical optics that we come across, it is an approximated one, it is not an actual one. We are making some approximation because in geometrical optics, we always say that the light travels in a straight line. But that is only valid when this condition it is getting fulfilled. And it is not always true. Na? Okay.
Yes, sir.
So it means this is an approximated one. We can say it is an approximated treatment. It is not an actual treatment.
Yes, sir.
So next part is reflection. So now there are two kinds of reflections. Okay. Now suppose light strikes the boundary of any two media. Suppose the light was going from air to glass or from water to oil. Then it strikes the boundary separating two media. And what happens at the boundary? That some part of the light it gets reflected and comes back in the same medium. Which diagram want to do?
So last one.
You have not attended EMT course earlier.
Yes, sir. I have attended.
Then you should know about this one. This is a single slit diffraction. This diagram is. What happens in single slit diffraction? There is a slit and there is a screen. So slit width I have taken as small a and distance of the screen I have taken as capital D. Now what happens during diffraction? Light, it bends around the corners and it appears in the region of geometrical shadow. And this is being represented by red line by me. Now what is the angular deviation? This theta is the angular deviation. And the deviation in terms of distance, it can be written as b minus a by 2 because the total deviation will be b minus a. But the total includes deviation along both sides, on the upper side of the center line and on the lower side of the center line. So it means half of it will be on the upper side and half of it will be on the lower side. Is it clear?
Yes, sir. Yes.
So that's what the deviation is. It means if this is the deviation, it means if I can represent this distance by b minus a by 2, and then tangent theta will be perpendicular by base. Now, see here. And tangent theta is nearly sine theta. And from diffraction, we know that sine theta is lambda by for first minima, isn't it? A sine theta equal to lambda.
Yes, sir.
So we have equated both, and then I got a value of b minus a by 2. So if this is negligible as compared to the original width of the slit, then we can say that there is negligible bending or deviation, or we can say that the light travels in straight line, and that's what we are getting, which you call as Fresnel distance. Okay. Clear?
Yes, sir.
So now let us study about reflection of light. A part of light is send back. I'm using the word send because right now we are defining the reflection. Okay. So this is how we define reflection, isn't it? So there are two kinds of reflections, regular and diffused. Now what happens during regular reflection?
Surface is smooth.
Yes. Smooth, plain, polished, whatever word you can use. Okay. So in this particular case, the reflection occurs in a particular direction. Okay. Negligible small, I mean to say that the reflection it occurs in a particular direction because it is a polished surface. Okay. Means this is how it occurs. No? Here is the intensity. But if you try to find the intensity along this, not there. Along this, not there. Like this. Okay. So it depends upon the incident direction of the incident ray. But in case of a diffuse reflection, it does not follow your law of reflection actually. It can go in any particular direction. Means all the rays they are not parallel. Even if the incident rays they are parallel, the reflected rays they are not parallel to each other.
Excuse me, sir.
Yes.
Sir, last line एक बार समझा सकते हैं क्या? Sir, previous slide की last line.
Last line ही मैंने बताई बेटा.
Yes, sir, but repeat please.
These are the incident rays. This is the surface. Now, after reflection, we will get all the reflected rays to be parallel. Na?
Yes, sir.
So where you are getting the intensity of reflected light in this particular area. Na? Okay. But if I ask you about this area, then what would be your answer? If I ask you about this area, what would be your answer? Okay.
Yes, sir. Now clear. Thank you.
You can understand it with a simple concept that if the incident rays are parallel, then the reflected rays will also be parallel. Okay.
Yes, sir.
But this is not so in case of diffuse reflection. Let me make the diagram in that particular case first of all, so that you are able to understand. This kind of surface is there. So all the incident rays are parallel. But what happens because of the roughness of the surface, they are subtending different angles at the surface. No? They all are not subtending same angle at the surface. Okay. So this ray, you can see the normal points out in this direction. So this goes this way after reflection, isn't it?
Yes, sir. यहाँ पे normal same है.
Yes. इस तरफ बन रहा है, you can see.
Yes, sir.
But here it is getting formed in this direction, so it will. So little bit change. No? So you can see they are not parallel, no? And here it is almost normal, no? Like this. So rays are actually crossing each other. You can see, isn't it? So this happens because of the roughness of the surface. Because incident light, it falls at different angles at different points on the surface. So actually, it follows that law I equal to R, but it appears that it is not following that because we disregard the roughness of the surface. Okay, or you can say we forget about the roughness of the surface. We just have a look at the incident and the reflected light. Yeah. What should we write in a short? In this case, if incident rays sorry. Paper, etc. So these are the examples of diffuse reflections. Okay.
Yes, sir.
That folded paper, especially, that is the perfect example. Now, everyone knows about the laws of reflection, I think.
Yes, sir.
What is the first law? Incident ray.
Reflected ray and the normal, they are in the same point.
Yes.
At the same point.
And the normal at the point of incidence. And this plane is called, what is the name? Plane of
Plane of
incidence.
incidence. Yes, sir.
It may also be called as plane of reflection. No?
Yes, sir.
This is the diagram. Okay.
Yes, sir.
And you can also represent these angles. This is the second law. These are the two laws. No?
Yes, sir.
Clear?
Yes, sir.
Let us actually try to prove that this I is equal to R. So this is the plane mirror, dash actually. A ray of light, it comes from point A, and after striking the mirror at point O, it gets reflected like this. This is I, this is R. Okay. Now let us assume that this is X and this is D minus X. and the total distance is d from A to B. Okay,
Yes, sir.
So which distance is D?
A to B,
Would be somewhat less. No? So
it is always the straight line distance. A to B means this distance, here to here. Suppose this is A. Okay, this is B. Clear? So let a ray of light coming from point A Now, what is the optical path between A and B? Do you know what optical path is?
The path traveled by the light,
Yes. And what
which
is that
is
path?
C into that's AO and OB. C into
A
B.
plus OB. Yes. And let us call this as L. Okay. Let us call this as L. Now, what is AO according to you? This is the right angle triangle. Okay. And perpendicular is A and base is X. Na? So it will be A square plus X square square root, isn't it? Similarly, OB will be B square plus B minus X whole square. Na? Please check. Now, according to Fermat principle, O will such that the optical path length is minimum or maximum, or you can say it is an extremum. Extremum means it may be minimum or maximum. And what is the condition for minimum and maximum? That the derivative of this should be 0.
Yes.
And obviously the unknown is X, and it means dl by dx should be 0. And from there we can get some condition. Okay. Please check this. And what are these quantities? Can you infer from the diagram that we have made? What is the quantity on the left hand side and the right hand side? Are you getting something from the diagram in terms of angles I and R?
Sin I equal to sin R.
Fine, sir.
Yes, very good. This is nothing but sin I, and this is nothing but sin R. It means I will be equal to R. Na? And you can see we have started with a random experiment. Na? Okay, and we have assumed the distances to be different, and then still we are getting the same answer, isn't it?
Yes. Yes, sir.
So it means now we are sure that this law will be applicable everywhere. Na?
Yes, sir. This is reflection. Na? And why it occurs? Anyone?
Because it slows down, the velocity changes.
Velocity changes. Yes, it is due to change in speed of light as it passes from one medium to another. If light okay, this is the special case. Na?
Yes, sir.
And how do you define the refractive index?
So mu.
I'm
Velocity of light in the medium to the velocity of light of the air.
velocity of light?
In the medium to the velocity of light in the air or fast medium.
No,
So the second one is the air or vacuum.
no, it's not correct.
The first one is air, second one is medium.
Yes.
So for the velocity and the reverse one, velocity case.
For the velocity, it is the reverse one. I'm not getting you.
So the velocity of the medium to the ratio of velocity of the medium to the velocity in refractive index.
No. Again, you are speaking the reverse one. It is always C by V. No?
Yes, sir.
It is denoted by. Can I denote it by N or should I denote it by mu? Anyone?
Whatever we prefer, sir. Either case, it's the same thing.
Oh, let us go with mu then. Because in EMT, we use this symbol for the permeability of the medium. So you people should not get confused, okay?
Okay, sir.
If someone is getting confused, then you can denote it by N. In most of the books, they denote it by N also. So mu is C by V all the time. Velocity of light in vacuum to the velocity of light in the medium.
Sir, what is the absolute refractive index?
What is
Absolute refractive index.
absolute refractive index? Absolute refractive index, obviously, it is with respect to this particular refractive index is called absolute one. But otherwise, you also have the ratio. No? You always have the comparison. No?
Yes, sir.
So more is the value of refractive index, more denser will be the medium. No? Denser will be the medium. And if the medium gets denser, then the velocity will reduce. No? If mu is more, then v will be less. No? You can see they share the inverse relation. No? Okay. Clear?
Yes, sir.
Yes, sir.
Now, what are the laws of reflection? How many laws are there?
So it's by taking off sensor that treated.
First law is again same like reflection. No? But the point is now we will replace reflected by reflected. No?
Yes, sir.
Plane of incidence or plane of reflection. Ratio of the sine of angle of incidence to the sine of angle of reflection, it is constant for any pair of media. No? Pair means there should be at least two media. No? This is called Snell's law. No? Reflection. Snell's law of reflection. Here R is the angle of reflection. Okay. So incident ray, normal, refracted ray. This is you can call it medium 1. This is medium 2. Obviously having different properties from medium 1. And refractive index of this medium you can represent by mu1, and for this to be by mu2. Okay. So sin I by sin R, you might have seen that it can be written as mu2 by mu1, isn't it?
Yes, sir.
Yes, sir.
And now mu2 will be C by V2. No? Mu1 will be C by V1. Can I write it as V1 by V2?
Yes, sir.
And V1 equal to F lambda 1 because we have studied that the frequency remains same. So this can also be written as lambda 1 by lambda 2. No? So you can see we are getting so many relations. No?
Yes, sir.
Okay.
Yes, sir.
So this is refractive index of medium 2 with respect to medium 1. This is called relative refractive index. This alone is called absolute one. Okay. Clear?
Yes, sir.
Now there are special cases for this, depending upon whether light goes from rarer to denser or denser to rarer, or it comes along the normal. for the normal incidence, I is 0, means R is 0. Am I right?
Yes, sir.
So light, it actually comes this way and continue following the same path. This is medium 1. Let me write it by different marker. So this is incident ray, this is refracted ray. Second case, when light goes from rarer to denser medium, it tends towards the normal, no? Like this. Like this. Actual, okay, this should be the, this was the expected one, but it moves this way, and this is called deviation, delta. Okay, this is called deviation, and obviously it is I minus R.
Yes, sir.
In this case, it is I minus R, and this was rare. Let me write with this is rarer medium. This is denser medium. Rarer denser means mu2 is greater than mu1. Okay.
Yes, sir.
So I mean to say I is greater than R. In this case, I is greater than R. Clear to everyone?
Yes, sir. Clear.
Now, when light goes from denser to rarer,
So away from normal.
yes, means in this case I will be less than R. So in this case, deviation is given by R minus I. Is it clear?
Yes, sir. Clear. So there was an article on a lateral shift that you might have studied in your lower classes when it passes through a glass slab. Do you remember?
Yes, sir. Yes, sir.
Yes, sir.
So I won't be writing the detail of that, okay? But I will be solving the mathematics concerned with that. Is it okay?
Yes, sir.
So here is a glass slab. Okay, so this is the straight line path, but it actually follows this path. Now suppose this medium is here, and obviously this is glass. Let's call this A, B, C, and this is the perpendicular N over here. Okay. What else do we require? Yes, refractive index of this and thickness of this. P is the thickness, and let's call it D, and this be D dash, and you can call it E, obviously. So this is the proper label diagram. So this is I minus R in this triangle BCN.
Yes.
Now, according to Snell's law, what do we have? Light is actually going from air to glass. So sin I by sin R, A mu G, isn't it? Please tell.
Yes, sir.
Okay, let us call this I dash instead of R dash. That will be much better.
because in fact this angle is equal to angle of incidence. No?
Yes,
So
sir.
please replace it by I dash rather than R dash. So Snell's law at point A, okay, that will be better at point A. So now, according to Snell's law at point C, sine R by sine I dash, it is equal to G mu A. Na? So number 2. Now A mu G is 1 by G mu A, isn't it? Inverse of that. Na?
Yes, sir.
So please substitute the values. So you will get that I is equal to I dash, and that's why I have drawn this ray parallel to this one. That's how we get this. Okay. Otherwise, I cannot make this ray parallel to the initial one.
So can you please go to the previous slide once?
Sine I by sine R. Now what is G mu A? So it will be 1 by sine R by sine I dash. So sine I by sine R is sine I dash by sine R. Okay. So hence,
Yes.
and this is called emergent ray. Do you know? This is called incident ray. And of course, in between is the refracted one. So hence, the emergent ray is parallel to the incident ray, but it is not along the same path. Na? So that's we call as lateral displacement. What is laterally displaced as shown in figure. And now we have to get the value of that lateral displacement or shift. Okay. And for that, from the diagram in this right angle triangle BCN, what is the value of sine I minus R? Can you tell me?
The CN by BC.
And what is CN?
CN is
That's a shift, no? CN
Yes.
is a shift.
yes, sir, CN is the
Yes, yes. So in right angle triangle BCN, sine of I minus R, it was CN by BC.
Yes.
Can I call it D? This is number 3. No? It means if I'm able to get the value of BC, then it will be done. No? And what is the value of BC? So that I can get from that triangle BEC. This is also a right angle triangle. So it will be cos R. No? Cos R is equal to BE by BC. And BE is what? T, no? Thickness. So BC is T by cos R. No? So from 3 and 4 we have P sine I minus R by cos R. So you can see the lateral displacement is proportional to the thickness of the slab. So if you are having two slabs, one is thin and other is thick, so the lateral displacement will be more in a thick slab. Isn't it?
yes, sir.
Can you please repeat?
Lateral displacement is proportional to thickness. Huh? So
Yes.
if you are having two slabs, one is thin, other is thick, then it will be more in a thick slab. No? It means
Okay, okay.
one is like this, other is like this. Okay, that's what I'm saying.
Okay, sir.
Now for small angles, for small I and R, cos R is nearly equal to 1. For very small, you can see. Cos 0 is 1. Na? And if angles are small, I minus R will be very, very small. So sin theta is equal to theta. Na?
Yes, sir.
Isn't it? So Cn will be P into I minus R by 1. Na? That is P I minus R. Na? So if I take I common, it will be 1 minus R by I. Na? Can I write this as mu? Because mu is sin I by sin R, and if the angles are small, it can be written as I by R. Na? Please check. So this is another relation for the lateral shift or the lateral displacement. If the angles are very small. Clear?
Yes, sir.
Yes, sir.
So this is very useful expression, and this can be straight away asked in exam also. That for small angles, what is the formula for the lateral shift or the lateral displacement? And in fact, this point also, I should write it here. Lateral displacement is proportional to the thickness of the slab. And in fact, you can write down that example that we have discussed. Thick and thin slab. Directly proportional. That is more appropriate.
So up to which angle we can consider it is a small angle?
Up to 5 degree, 3, 4, 5 degree, 0, 1, 2, 3, 4, 5, small. You might have heard the word grazing. No? In the books, I defined this word in solid state physics. Grazing is near to the surface. And when they use this word grazing, it means the angle made by the ray with the surface is very, very small. It is like this. It is nearly parallel to the surface, you can say, like this. Okay, so in that scenario, angles are very, very small. With the surface, of course.
Glazing and glancing are the same, I believe.
Yes, yes, they are same.
Okay.
Clear? So we will end our discussion here. That's all for today. So we will continue from here tomorrow, and we will discuss some other fundas about the reflection and in fact, a lot of numerical problems. Okay, students, bye-bye. Take care.
Thank you, sir.
Thank you, sir.